let's take a quick delve into the world of energy. First up, what is energy? Well, energy is a measure of the ability of something to do work. Units for energy are the joule. The symbol of the joule is the capital J. Now, if we had lots of joules, we would simply put a prefix in front. So we could talk about kilojoules or megajoules or gigajoules, terajoules, etc. If we didn't have many joules at all, if we just had fractions of joules, well, then we could talk about millijoules or microjoules. But joule is the base unit of energy. Now, there are 9 forms of energy, and they can be broadly divided into potential energy and kinetic energy. Potential meaning stored. The energy is stored somehow. It's not actually being released yet. So let's look at potential energy first, the energy that's stored in things. We have gravitational potential energy, chemical potential energy, elastic potential energy, and nuclear energy. You'll note we don't generally say nuclear potential energy, but nuclear energy is one of the stored, the potential forms of energy. Now, we'll go through each of these one by one in just a sec, but first let's check off the kinetic energy forms. There are 5 of these. We have kinetic energy, Ke, heat, electrical energy, sound, and light. Let's go through these one by one now, starting with the potential energy forms. So first up, gravitational potential energy. Now, this is a form of energy that's stored due to being lifted up against gravity. So anything that has been lifted up has gravitational potential energy. Anything like a walrus on top of a cliff, the walrus expended energy to get up there, so that energy is now stored in the walrus. If the walrus were to fall off the cliff, that gravitational potential energy would be released. Okay, so anything that's being lifted up against gravity has GPE, gravitational potential energy. Another example might be a pencil standing on its end, the water at the top of a waterfall, etc. Anything lifted up against gravity. Now, actually, we have a nice little equation to calculate the GPE of an object. It depends on the mass. Something with a bigger mass will have more GPE. It also depends on the height to which it was lifted up against gravity. So the equation, which we'll get to in another video, is actually quite simple. It's just the GPE equals the mass times the height times gravity. But as I mentioned, we'll look at that in another video on the calculations involved with energy. But for now, let's move on to chemical potential energy, CPE. Now, also a form of stored energy, right? That's that potential in its name. That means it's stored. CPE is the energy that's stored in the chemical bonds of all substances. So this means that all substances have this form of energy. Like in terms of the gravitational potential energy, not necessarily everything has that. If something's sitting on the ground, it doesn't have any GPE because it hasn't been lifted up against gravity, right? But anything, no matter where it is, has CPE, has this chemical potential energy. And this energy can be released from fuels when they are burned. We get that heat and light released. As chemical bonds are broken, energy gets released. Okay, next up we have elastic potential energy. Another form of stored energy. It has the word potential in its name, so dead giveaway there. This is the energy possessed by things when they are compressed or twisted, flexed, or in some way wound up. So objects with EPE might include a bow that is about to be fired. The drawstring has been pulled back. Maybe you're bending your ruler and it doesn't really want to be bent, so if you let it go, it would straighten again. So these are things that have elastic potential energy. Essentially, they will return to their original shape. Think of a rubber band, right? An elastic band. Why is it called an elastic band? Not because you can stretch it, but because when you let it go, it returns to its original shape. Right? That's due to its elastic potential energy. Now, the other potential energy is the nuclear energy, and remember, this doesn't get the word potential put in its name, but it is another form of potential energy. Now, this is the energy released when the structure of atoms is changed. Now, this could be changed in a couple of ways. Firstly, an atom could be split. This is what we call fission, and we can actually do this, so go us, technology, great. Or it could involve atoms being fused together, and this is called fusion. This is not something that we can do yet. This is done in stars. This is how stars get their energy, but we are actually trying to do fusion. but you need plasma at like 100 million degrees Celsius, and that's really quite hard to control. So we're not really there yet with the whole fusion energy, but we are on our way. Our technology is getting better. Now, the good thing about nuclear energy is that if controlled, it can be used to produce large amounts of heat, which can then do things like boil water, which gets converted to steam, which we can pass through turbines to create electrical energy. So through the use of nuclear energy, we can get a lot of the stuff that we want, i.e. electrical energy. If it's controlled, that's great. If it's uncontrolled, it can be very disastrous. Now, this is one of the reasons why we're trying to do fusion, because we don't get things like nuclear meltdowns or anything like that. It's actually much safer doing fusion than it is to do fission. So we can do fission at the moment. We are trying to do fusion. Right, so let's move on to the kinetic forms of energy. The first one, funnily enough, called kinetic energy. So this is the energy possessed by anything that is moving, anything at all. If an object is moving, it has kinetic energy. Now that might be from a train to a leaf falling to a swimming fish or a person running along. Anything that is moving possesses kinetic energy. Now I mentioned I'll make a follow-up video to this on calculations of energy. We have a formula for this as well, an equation for working out the kinetic energy. That's Ke, so kinetic energy, is equal to half times the mass times the square of the velocity. So Ke equals half mv squared. So it does depend on the mass. If two objects are going at the same velocity, the one with the larger mass will have more kinetic energy, and it also depends on the square of the velocity. So if the same object is suddenly going faster, it will now have more kinetic energy. All right, so the next one is heat energy. Now this is actually a special form of kinetic energy. This is possessed by matter because of the movement of the particles. All right, so remember, in a solid, the particles, they're not just sitting there, they're vibrating on the spot. In a liquid, they have more energy, so they're moving around more, and in a gas, they have even more energy. And we can measure this in terms of temperature. Temperature is simply a measure of the kinetic energy that the particles of a substance have, right? So heat really is a special form of kinetic energy. It travels through solid matter by conduction, through fluids, so that's a liquid or a gas, through convection, and through gases and through a vacuum by radiation. Now, next form of kinetic energy is electrical energy. Now, this is due to charged particles. I guess the most useful form of this energy would be electrical current. That's a flow of charges. Often, but not always, electrons, right? So we often talk about electrical current being the flow of electrons. Well, they don't have to be electrons. It just has to be charges, from one place to another. If they're moving in the same direction, we tend to say that's electric current. So appliances like toasters, radios, ovens, motors, etc., they all use this form of energy, this electrical energy. So the next one, sound energy. Well, this is energy which travels through matter by longitudinal waves, or also known as compression waves. Now, sound won't actually travel through a vacuum because there's no matter to carry the waves, right? So sound energy is the energy traveling through matter. If there's no matter, then the sound wave can't continue, which led to this very famous catchphrase for the movie Alien: "In space, no one can hear you scream." Right? Because there's nothing for the sound wave to travel through, which I guess is actually quite a good thing, because otherwise, if we could, hear the sun, that might blow our eardrums up straight away, because the sun, I imagine, would be a really, really loud object, right? So it's good that sound can't actually travel through space, right? Can't travel through a vacuum. Now, any vibrating object will actually produce sound energy. So it might be a violin string, guitar string, the skin of a drum, etc. So any vibrating thing creates sound energy. Anything which is vibrating, because sound energy is a compression wave or a longitudinal wave, and longitudinal waves, the medium that the wave is passing through moves in a back and forth motion, so essentially vibrating. Another form of kinetic energy is light energy. Now, this is a form of electromagnetic energy. Remember, there are lots of different forms of electromagnetic energy, from radio waves through to visible light, right up to gamma radiation at the other end. Now, we need this light energy to see. That's always good for us. Plants use it for photosynthesis. We can use laser light to, cut through thick steel or perform delicate eye surgery with LASIK surgery. We bounce lasers off the moon to measure the distance to the moon, etc. So that's light energy in use there. Right, so they are the 9 forms of energy broken into the 2, overarching forms of potential energy that is stored versus kinetic energy. Now we have this thing called the law of conservation of energy. Right? Now, essentially, energy can be transformed from one type to another. That is not a problem at all. Okay, energy is easily converted from one type to another. Like if you say, if it's a cold day and you're walking to school and it's winter, so you rub your hands together. Why do you do that? To warm them up. Yes, well, you've just converted from kinetic energy, the movement of your hands. Right? Now there's friction between them and that generates heat. So we've converted from kinetic energy to heat energy. So we can quite happily transform or change one form of energy into another form. However, it cannot be created or destroyed. The amount of energy you start with doesn't change. Okay, you can't just magic up some more energy, or if you're feeling too energetic, just delete some. No, you can't do that. So we can change between the types of energy, but we can't actually get rid of any energy or suddenly make some more. It is conserved. The amount of energy, the total amount of energy, is always conserved. Now, we mentioned the transformation of energy. We can quite happily change from one form to another. However, since it's conserved and can be quite easily transformed or converted, that means that if something is to gain energy, that energy had to come from something else, okay? Because, as we just said, it's conserved. We can't just make more energy. So if something gets more energy, it didn't just magic it up. It got that energy from something else. Something else had to lose energy. So let's take a quick look at energy being converted from one type to another. Now, in this picture, the idea is what I've already mentioned, rubbing your hands when you're cold. Okay, so that converts the kinetic energy into heat energy. But let's take a look at some others that I haven't actually mentioned yet. So the next one, we have a steam train. Pause the video and just think to yourself, what could the energy start as and what could it be converted into? Okay, so for a steam engine, we are converting heat energy into, well, what does the train want to do? It wants to move along. That's right, we're converting it into kinetic energy. So from heat to kinetic energy. All right, next one. How about using a Bunsen? Once again, pause the video, have a quick think. Okay, so with a Bunsen, we are burning a fuel. Okay, so the fuel has chemical potential energy, and when we burn it, we release that energy. Now, a couple of forms. If you had a heating flame is often called a roaring flame because it's quite loud. So we're getting sound energy. If you do it in a dark room, the Bunsen will help you see, so we're getting light energy. But really, what do we use a Bunsen for? We use it to heat things. So really, we're talking a conversion from chemical potential energy into heat energy. All right, next one. Maybe you have a tin of nails and you shake it. Pause and think. And unpause. Okay, so you're shaking the tin. That's movement, isn't it? So we're starting with kinetic energy, and it's nails in a tin. That's going to make a bit of a racket. So we're converting kinetic energy into sound energy. Next one, a petrol-driven car. Pause, think. Okay, so it's a petrol-driven car. It's run on petrol. That is a fuel. So as a fuel, we're talking about the kinetic potential energy, right, stored in the fuel. And then when that fuel gets burned, that gets released. But what's the aim of this car? Is to move along. So we're getting kinetic energy out the other end. So we're converting chemical potential energy to kinetic energy. Now, what about a battery? Have a quick think. Okay, with the battery, again, the energy starts as chemical potential energy, but we're not after the battery moving along. We don't want kinetic energy in this case. We want electrical energy. So we're converting chemical potential energy to electrical energy. Next one, what about photosynthesis? What does the energy start as? What is it converted into? Have a think. All right, so remember the process is called photosynthesis. Photic, photo, any of these prefixes should say to you light, right? Photosynthesis, using light to make something. In this case, the plants are making their own food. So we're starting with light energy, right? That's the photo part. And the synthesis part is that the plants are making their own food. The energy gets stored in the chemical bonds of the starch, etc., that the plants are making. So that's converting light energy into chemical potential energy. What about using an electric light? Have a quick think. Okay, so using an electric light, we must be starting with electrical energy. And why do we turn the lights on at night? So we can see. There we go. So we want to get light energy out the other end. So conversion of electrical energy to light energy. And the last one, let's talk about burning magnesium ribbon. You may have done this in the lab at some stage, and your teacher probably warned you, don't look at the light, because it's a very bright light, and probably you did, and saw spots afterwards for a couple of minutes. But anyway, when you burn magnesium ribbon, what is the transformation of energy that takes place? Well, in this case, it would be chemical potential energy because we're burning something. Essentially, the magnesium is like a fuel. We are releasing the energy when we break the chemical bonds, and we're getting a lot of light. We also get heat energy, sure, but the point is it glows very bright, a nice bright light. So we're converting our chemical potential energy into light energy. Now, we can actually trace energy back. Right? The energy in something can be traced back, and we call this an energy chain. So if we think of a person running, what energy do they have? Well, they're running along. They have kinetic energy because they're moving along, yes? But how did they get that energy? Remember, you can't just magic up some energy. If you're getting more energy, you have to get it somewhere. Well, the person got their energy by the respiration of food through cellular respiration. They had a big breakfast that morning, gave them lots of energy to go for the run. But where did the energy in the food come from before then? Well, the food has chemical potential energy obtained through photosynthesis using sunlight. Okay, but where did that energy come from? Well, the sun got its energy by nuclear reactions, nuclear fusion reactions. So this is what we refer to as an energy chain now. We can say that we started with some nuclear energy in the sun, and that got converted into light energy, which the plant used to make its own food and stored it as chemical potential energy. And then the person converted that energy into kinetic energy when they went for a run. So this is an energy chain. We're sort of tracing the movement of energy through a number of systems, right? From being converted from one type into another, into another, into another. And I guess from the person running, we would then convert that energy into heat energy, because when you go for a run, you get hot, right? Now, from that heat, that would, I guess, be the end of the chain. Heat energy is often a waste of energy, right? That's how energy gets wasted. When you convert something to heat, that's often not what you want. Like the example of a light bulb, we want light. So, we turn the lights on, we can see, that's great. But when we leave the light on for a little while, it actually gets hot. Now, we don't turn the light on to make heat. Right? That's what our heaters are for, not our light bulbs. But we do get heat. So that's sort of like wasted energy. Energy is often wasted from a system as heat. So in this case, I guess when the person goes for a run, they're going to get hot. The energy is now going to be dissipated out to the universe and wasted as heat energy. So that's a quick look at energy and how it can be transformed from one type to another, whilst of course maintaining the conservation of energy.
Like the video, punch that like button. Want to see more videos? Smash that subscribe.